All right, good evening, everyone. Okay, I see I forgot to put this up for download. Okay, there you guys can download it now. All right, I believe last week we did start with module 5. So I think we looked at, yeah, if I remember correctly, we pretty much managed to get to the RC coupling circuit, I think. Yeah, I remember us getting up to this point. Okay, so yeah, so I'm not going to go through that again. I'll quickly go through the inductor and then harmonics. And then I'm pretty much just going to jump into examples with RLC circuits. I'm not going to, you guys will see the slides have a few examples in here. So I would recommend that you guys go through that. And I would like us to just quickly take a look at resonance as well. There's a few examples in the textbook on this that I would ideally like us to go through as well. As well as I think what I will do is I'll go through the example here in the slides as well. And something that I don't really explain in the slides is selectivity. So I actually ideally want to go through that as well. Okay, so yeah, so let's quickly just take a look at harmonics and the behavior of an RL circuit with time constant, or rather the transient response of an RL circuit. Right, so if we take a look at an inductor, so if you guys can remember the factors influencing the energy stored on a capacitor and its capacitance was pretty much the dielectric constant, cross-sectional area of the plates, the cross-sectional area, okay, yeah, so, and the distance between the plates. So those three things pretty much are going to influence your, that's considered your internal factors that will influence the capacity or the capacitance of your capacitor. And then external influences or external factors, that's then going to determine the amount of charge stored on your capacitor. That's going to be external factors. That's going to be your voltage applied to the capacitor. Right, so then for an inductor, in this case, the external factors are going to be current, and internal factors are going to be the number of turns, cross-sectional area of your core, permeability of your core material, and the length of your conductor of your inductor, if I put it that way. But that's the same as your number of turns, essentially. All right, and then essentially the external factors here determining the strength of the magnetic field or the inductance of your inductor. Rather, yeah, you can actually say the energy stored in it or the magnetic field strength. That's going to be the current. That's going to be the determining factor there, or the external factor. Right, so the energy stored in an inductor, very similar to that of a capacitor, except this formula is incorrect. I'm pretty yeah, now I'm pretty sure my corrected slides I have bungled somewhere, or hid them from myself. In any case, that formula needs to be L times I squared over 2. So it's very similar to the capacitance, where it was the capacitance multiplied by the voltage squared over 2. Right, so inductor is just going to be inductance and current. Right. Again, the curves for voltage and current is going to look very similar to that of the capacitor, but now the dynamics are a little bit different. So whereby a capacitor sort of opposed change in voltage over it, an inductor is going to impose change in current through it. Right, so it's essentially how you can view it is, if you take, for instance, if you drink cold drink with a straw, a straight straw, you're just going to have almost immediately just liquid flowing through that straw. with a straw that's coiled up, or if you have a long, one of those little crazy straws that make the weird turns and stuff, liquid is going to take a longer time to flow through that straw, and is also going to be a little bit more difficult, right? So it's almost, yeah, so you can almost, you guys, I hope you guys can see almost where this whole thing of reactance comes from as well. It's basically due to the characteristics of capacitors and inductors that they show with voltage and current. Right, so this circuit that we have here, so at the moment that we switch this on, so in the beginning, you essentially going to have um, zero current flowing in the circuit, right? So there's not going to be any current flowing, and your voltage is going to be at a maximum. Now, as the current starts flowing through the circuit, the voltage across your inductor, yeah, so I actually failed to mention that voltage there is the voltage across your inductor. So as the current is increasing, the voltage is also going to decrease at the same rate. Right. So the current will then increase to a maximum, whereby the voltage will then decrease to a minimum. So then you're going to end up with a situation where your supply voltage is essentially going to be applied to your resistor, and your inductor is going to act like a short circuit. Right, so again, we have this whole concept of time constant. And again, the circuit is considered to be at steady state, so this point here, once we get to 5 time constants. And the time constant for an RL circuit is then defined as the inductance divided by the resistance. Again, note the unit here is in seconds. And yeah, so very similar theory, or very similar ideas behind this circuit as what we had with the RC circuit. Again, at any point in time, the inductor and resistor voltage added together will give you your supply voltage. So this is your supply voltage. So if we go take a look at, let's say, 3 time constants, for instance, so the voltage there and the voltage there added together, that will give you your supply voltage. Right, so you guys also see that the current and the voltage across the resistor will also follow the same curve. Right, so this curve here is not just, this is not just your current, but it's also your voltage across your resistor. Okay, and you can also discharge the inductor. There is a problem with this curve, however. This curve is wrong. Or is it this? No, that one is actually, sorry, no, that one is actually, yeah, that one is actually fine, sorry. This curve here, this one is wrong. Your current, your current can't go to a maximum when there's no source. It actually needs to look something like this. Right. Or your voltage across your inductor will look something like that. So essentially for discharge, let me go back to the circuit. So when we're discharging, basically have a short circuit here. Now, the assumption with discharge is that the inductor is fully energized. So essentially, in keeping with Lenz's law, the inductor, with the magnetic field now collapsing, we're going to have a change in voltage polarity here. So the voltage is going to switch polarity, and the inductor is going to keep on pushing current in the same direction. Right, so that's actually why that actually was right. Both these curves are incorrect. That actually needs to decrease like that. There we go. Okay, that's right. So essentially what happens is during discharge is your voltage is going to be a maximum in the beginning, but it's going to be changed in polarity like we have there. and your current is also, so remember the current didn't stop flowing, right? So the inductor got energized to its maximum. Now the current is just going to keep on flowing due to the collapsing magnetic field. So your inductor is essentially acting as a source. So your current is just going to then decrease as your voltage from on your inductor also decreases. Right. Okay, so any questions up until this point? Now you guys are not really going to do any calculations on this. Pretty much just a little bit of theory, just need to know what the curves look like. And that's about it. And harmonics. Okay, so harmonics actually, this is actually more to do with non-sinusoidal waveforms. So I'm going to give you guys a small little history lesson in electrical engineering here. So a guy with the name Fourier, I think that Fourier is the more correct pronunciation, was a Frenchman. He discovered that um, he discovered mathematically that different functions, so it doesn't necessarily have to be a sine function. So things like, for instance, square wave forms or triangular waveforms, even things like parabolas, and if you can make it a periodic signal somehow, can all be um, built out of sine waves, right? So, and it was actually proven to be correct. So if you go measure a square waveform on an oscilloscope and you zoom in really closely to the edges of the square wave, you will see these little ripples actually. So yeah, and you can actually use we actually use Fourier's ideas when we design filters to filter out high and low frequencies from a signal. All right, so but in any case, so what a harmonic is basically a component of your frequency of a specific signal that is an integer multiple of the fundamental frequency. Right, so your fundamental frequency is essentially the frequency of your signal that you can measure. And then the harmonics will have frequencies then of 2 times the fundamental, 3 times the fundamental, 4 times the fundamental, and so on. But not all signals have the same fundamental frequencies. Now, you guys also note that harmonics are also periodic at the fundamental frequency. So essentially what that means is that if we take a square wave, for instance, now, so I'm going to kind of jump ahead here. So with a square wave, you guys will see that the fundamental frequency is, well, basically the frequency of the square wave itself. So basically this turquoise waveform is a square wave constructed out of 3 sine waves, essentially. And the harmonics for a square wave will be odd harmonics. So third, fifth, seventh, ninth, and so on. So basically what this means is, so the third harmonic, for instance, so if we take a look at the third harmonic, which is this wave here, so you guys will see why. Okay, so what it means for that harmonic to be periodic at the fundamental frequency means that if the fundamental frequency is, let's say, 50 hertz, then the third harmonic is going to be 150 hertz. So basically, you'll see you'll have, so if we take a look in one half wave of the fundamental, you're going to have 3 half waves for the third. Or if you look over the whole cycle, so for one waveform, you're going to have 3 waveforms for the third harmonic. And you can see the same thing with the fifth as well. So the fifth is then going to be the smaller one. And you guys should also notice a trend here. is that the harmonics is also their magnitude is the reciprocal of, not really the reciprocal, how can I put this? So it diminishes by the harmonic. So what basically what I mean is that if you look at the third harmonic, for instance, the third harmonic is a third of the fundamentals magnitude. It's the same going to be the same with the fifth as well. So the fifth harmonic is going to be a fifth of the fundamentals magnitude. Same with the seventh, same with the ninth. And just so by the way, I'm just going to add this here for a triangular waveform. That's going to be all the even. That's going to be all the even harmonics, right? So you're going to have your fundamental, and then 2F, 4F, and so on. Now, we can't really use sine waves to observe any frequency or phase disturbances, because the only thing that's going to happen with a sine wave, if you input a sine wave and you change the frequency or you change your circuit parameters, all that a sine wave is going to show you is a phase displacement or maybe a change in frequency, and that's about it. You're not gonna get any information out of that in terms of whether your circuit has a high frequency response or let me put it this way, a good high frequency response or a good low frequency response or bad responses in terms of those frequencies. So essentially, if you take a square wave, so essentially what's happening is you are playing around now with the harmonics here. So you're either filtering them out or introducing extra harmonics into the system. Maybe some of them phase shifted. But anyways, if you, for instance, get distortion on the slopes of your square wave. So remember, your square wave is not perfectly square. It is somewhat sloped on the edges. So if you get any deformation there, that's going to give you some indication on the high frequency response of your system. So that will usually show a shortage of high frequency response. And if you have any deformation, so usually the slope would get more pronounced with a shortage of high frequency response. And if you get any deformation of your of that flat of the basically the maximum and minima on your square wave, that's an indication of low frequency response or shortage of low frequency response. So basically your circuit is filtering out some of your lower frequencies. Okay. Right, so a very typical exam question on this is pretty much drawing the square waveform consisting out of its harmonics, and then and then getting asked to draw the third, fifth, and seventh harmonic. That's pretty much the worst you guys could get, I think, in terms of harmonics. All right. Okay, so just go through this, guys. It's pretty much, this is just repeating basically what we have looked at here. Okay, then we have RLC networks. So for this subject, you guys are going to definitely get mixed RLC networks. So I'm not going to, there's not really any theory around this, so I'm just going to skip through this. So you guys can go through the examples here in the slides. I'll do one of the examples from the textbook now with you guys in class. Before I do so, let's quickly go through resonance as well. Right, so so for resonance, again, RLC circuits, if we take a look at a a series RLC circuit, but this is also true for a parallel circuit as well. So your circuit will go into resonance when your inductive reactance and capacitive reactance is equal to one another. So essentially, from the point of view of your source, at least, the capacitor and inductor isn't really there, or rather, it doesn't consider. Yeah, if it was sentient, it would not consider them being there. So they're essentially canceling each other out. Now, in a series circuit, what that essentially means is that the voltage across your inductor is going to be the same magnitude as the voltage across your capacitor, but they're going to be 180 degrees out of phase with one another, so they're going to cancel each other out. Right. So meaning VL and VC is also going to be equal to one another. Right, so basically what that means for us, so the first part here, the resonant frequency, we can go and calculate with that formula there. Again, the condition that XL and XC need to be equal. That also implies that the voltages across both these components will also be equal, and that your source voltage is now going to sit across your resistor, and your impedance is then going to be a minimum. So your impedance is going to essentially be just your resistance, and your phase angle in this case is also going to be 0, which also means your power factor is 1. And your current is then going to be a maximum because, well, your impedance is a minimum. Okay, so if we take a look at the what the impedance will do as frequency changes. So at low frequencies, your circuit is going to act like a RC circuit. So it's going to have a leading power factor, leading phase angle. So pretty much going to act like a capacitor. And then frequencies above the resonant frequency, your circuit is going to act like an inductive circuit, so or more like an RL circuit. Right, so you guys will see then at very high frequencies. So as the frequency tend toward infinity, basically your yeah, it's essentially then you basically making your circuit an inductor in that sense. Right, so what the current response looks like. So for current, so as the frequency, so you guys will see as the frequency increases towards the resonant frequency, the current is also going to increase, and then you're going to get a maximum current there. And then as the frequency then increases past the resonant frequency, that's then going to decrease the current as well. Now, I don't know if you guys went and read through chapter 3 with the filters. So you guys will kind of notice that we somewhat sitting here with somewhat of something of a bandpass filter here. So if you were to change the current here on the y-axis to a dB scale, and you take the -3 dB point here, basically going to sit here with a bandpass or band select filter or frequency select filter. So you get something like this. All right, so I'll explain in a moment. So this is going to tie in with things like bandwidth and selectivity and such. Then, yeah, so there's the proofs for conditions for resonance. Not really going to go through this. Kind of already explained it. Parallel resonance. So what actually happens here is you have current circulating between your inductor and capacitor. That's essentially, those currents are going to be equal to one another. And yeah, so basically with a resonant parallel circuit, you just have energy exchange the whole time between your inductor and capacitor. And from the point of view of your source, yeah, that might have well been an open circuit. Right, so if we take a look at some of the values here, again, resonant frequency, we'll know how to calculate that by now, I hope. Inductive reactance, same as your capacitive reactance, so that's kind of the requirement for resonance. But now in a parallel circuit, that implies that the current through the inductor and the current through the capacitor is going to be the same. Your total current is going to be the same current going through your resistance. And in this case, yeah, so in this case, your current is going to be a minimum because your impedance is going to be a maximum, right? So your impedance is going to increase. So, and by default, your current is then going to decrease. Again, phase angle is going to be 0 degrees, which also implies that your power factor is going to be 1. And yeah, so there are your curves. So first up that we have here is the impedance. So as the frequency is increased from 0 towards the resonant frequency, so before you reach the resonant frequency, your circuit is going to act like an inductive circuit, and then increasing the frequency past the resonant frequency, that's going to then force your circuit to act as a capacitor or RC circuit. And if we take a look at the current response, essentially, yeah, so you guys will see at low frequencies, the current is going to be really high, and at high frequencies, the current is also going to be really high. But at resonance, the current is going to be really low. Now, again, you can again change the scale here, or rather the y-axis here, to be dBs or gain or whatever. And then you can take your minus 3 dB principle here again. In this sense, yeah, this sense is going to be a little bit more difficult to get that half power frequency on this curve, but you can probably estimate it around about there. Say minus 3 dB. Okay, minus 3 dB. And you guys will notice that that is essentially a band reject filter. So yeah, so that's essentially what we're sitting with here. Okay, then we sit with Q factor and bandwidth. Now, Q factor, so yeah, so with filters, you guys should have seen already what bandwidth is defined as. And we did speak a little bit about it, I think, with the operational amplifiers. Now, Q factor, also called your magnification factor, that's essentially going to be your inductive or capacitive reactance divided by your resistance. Or you can just show it, yeah, or you can go going, so yeah, you have two formulas there to go and calculate it. And yeah, so at resonance, essentially, doesn't matter whether you use the inductive or capacitive reactance. And again, series networks, the inductor voltage and capacitor voltage are going to be the same. And how to calculate those voltages, basically the source voltage multiplied by the Q factor. And then it's the same for current in parallel networks. If you want to go calculate inductor or capacitor current, that's your total current times Q factor. Right, so there is a bit of a explanation here on what bandwidth is. So bandwidth is the range of frequencies between F1 and F2, or on the drawing here between FL and FH, where FL is your lower frequency and FH is your upper or higher frequency. And again, this is determined at your half power point of your amplifier or of your circuit here. And that's at the minus 3 dB point. And yeah, so the points where the bandwidth is then taken are known as your half power points. And we can go and calculate bandwidth then with either one of these formulas. Another way to calculate bandwidth, if you know what the lower and upper frequencies are, there is actually an example in the textbook of this. It's not FL, that's FH minus FL. It will also give you your bandwidth. And then you can actually also go and calculate FL and FH using the resonant frequency. So FL is essentially then the so that's going to be the resonant frequency minus the bandwidth over 2, and FH is then going to be your resonant frequency plus bandwidth over 2. Right, so that's also actually a range of formulas that you can use there to work with the bandwidth. So there's a bit of an example making use of Q factor. And yeah. So one more thing that I just quickly want to explain, I'm just going to use the whiteboard for this. And that's the idea behind selectivity and bandwidth. Okay, so if I take, for instance, so I'm just going to do this by hand real quick. Oh, goodness. Okay, let's use the tools in our disposal here. It's going to make it much easier. Okay, so I'm going to, so let me maybe do 2 waveforms here for us. There, change the color, let's make this one red. Okay, and then let's put in another one. And we make this one blue. And let's maybe make it the same amplitude. But okay, I think let's make this a wee bit narrower. Right. Okay. So so which of these two responses do you guys say has higher selectivity? The blue one or the red one? Which one is more selective? Okay, so I have 2 different answers here. So I'm not going to say who's right and who's wrong just yet. Right, so, okay, so these maximums, or rather you can actually view this as your gain as well. So these sit at the resonant frequency. So let's write that down. And then let's take a look at the minus 3 dB point. I am going to say it's, so actually, so the point of, so this thing actually discriminates very nicely. Right, so I'm going to say that it's there about, and then, no, not what I wanted to do. So I'll do it this way. So that's there. Okay, so there's your lower and upper frequencies for red. So let me maybe write that in red. And then you also have for blue as well. That's going to sit there. Okay, so this is going to sound very counterintuitive for some of you. Right, so you guys will see that blue has a small bandwidth and red is a very wide bandwidth. Right, so wide bandwidth means that you have more frequencies being passed, right? And a narrower bandwidth means you have less frequencies being passed. Right, so remember here on the x-axis, this is frequency, and this is essentially our gain on the y-axis. Right, so selectivity comes, so basically selectivity has to do with either having a wide or narrow bandwidth. So a signal with a narrow bandwidth has a very high selectivity. Right, so basically what that means is your blue curve here, or the blue response, has a high selectivity. Because you basically, how you can view it is it selects specific frequencies. So if you think about the radio in your car, for instance, right, you're not listening to 3 or 5 radio stations at a time. You're only listening to one radio station. You only zone in on one frequency, right? So only one frequency is selected there. Whereby if you look at the red response, you have a wide range of frequencies within that response. So the selectivity is very low. So you're not selecting one frequency, you're basically selecting a whole bunch. High selectivity versus low selectivity, there's not really a good and a bad there. It depends on your application. So for instance, if you want a radio to work properly, you're going to need an amplifier circuit or a receiver circuit that has a very high selectivity so that you don't listen to 3 or 4 or 5 radio stations at the same time. And for red, that would be probably, if I can maybe use a very stupid example, it's actually not really done that, well, it's actually still done in asymmetric warfare. It's basically it's also again kind of a radio application or communications application, but if you want, let's say you want to listen in on your enemy's radio conversations, then you just widen the band of frequencies that you're receiving. You're obviously going to receive a whole bunch of other nonsense as well, but then you have to kind of then listen and see if you can find uh, what the where somebody is talking, and then basically maybe zone in on that frequency. But anyways, that's pretty much what I have here for you guys. So high selectivity is the blue, so you have a narrow bandwidth. Low selectivity is the red, white bandwidth. Right. Yeah, and I think your time is actually catching up with us here. I don't know if I'm going to. I think I'm going to do a first a bandwidth example because I don't think you guys have really done lots on this or on that. In terms of RLC circuits, I mean, this is pretty much just a continuation of N4 level RLC circuits. And like I said, I have numerous examples here on the slides. You guys, please go take a look at these. But yeah, let me maybe quickly do us a bandwidth example. In fact, I want to do one that's a little bit more difficult than the example I have here. Okay, so just give me a few seconds here to get us an example from the textbook. Well, this one is not as hard, but I mean, the example I have in the slides is pretty much 5.3. We can take a look at 5.2 here. Let me copy this in. Okay, right, so we're given a series RLC network with the following component values, and they're connected across an alternating current supply, resistance of 200 ohms, an inductance of 0.15 henries, and a capacitance of 60 microfarad. Right, so essentially, yeah, so we need to use the information then given to us here to determine the lower and upper half power frequencies. Right, so for a start, the bandwidth is one of the things that we can go and calculate. So I'm just going to quickly take a sneak peek here at the formula. So the formula that's also given here is that the bandwidth is equal to the resistance divided by 2 pi L. And I think I'll just do this, fix this real quick. Bandwidth. So the resistance here is then 200 ohms divided by 2 pi divided by L, which is 0.15. That's essentially 100 divided by just reset my phone's calculator here. So that's 100 divided by 0.15 pi. Right, so that will give you 212.205 hertz of bandwidth. Right, so that's done. But now we need the upper and lower frequencies. Right, so for the upper frequency, so that's just going to be your bandwidth divided by 2 plus your resonant frequency. The resonant frequency we can go and calculate as well. So that's going to be 1 over 2 pi square root LC. That's 0.15 times 60 times 10 to the minus 6 under the square root there. That is then 2 times pi times square root 0.15 times 60 divided effectively by a million. Close brackets. That's going to give you a resonant frequency of 53.052 hertz. Right, so now we can actually go and calculate our upper frequency and our lower frequency. That's then the 212.205 there divided by 2 plus the resonant frequency of 53.052. Let's calculate this. So 53.052 plus 212 0.205 divided by 2 there. That's going to give you an upper frequency here of, so there's a bit of a, I see there is a bit of a problem here. I think I might have calculated this incorrectly. Check now. That's going to give you 159.154. Just make 100% sure. There's actually a problem with this example, with this exercise. Actually, notice it now. I think that bandwidth was 2 pi times L, R over 2 pi times L. I don't think that thing is a very reliable formula to use. I want to see if there is not anything else that we can use here instead of that. Yeah, okay, well, it looks like we are stuck with that option of ours. I think maybe let me just recalculate the resonant frequency. I might have made a mistake there. So that's 1 divided by bracket 2 times pi times bracket square root of 0.15 times 60 divided by a million. Close the bracket, close the other bracket, close the other bracket. Okay, I'm getting 53.053 hertz there. Let's make sure we calculated the bandwidth correctly. 200 divided by 2 divided by pi divided by 0.515. It's 212. Yeah, there is a bit of a problem here, but in any case, but let's just follow the exercise for exercise sake. Right, so that's your upper frequency. So you guys will see with the lower frequency, we're going to get a negative number, which shouldn't be, because negative frequencies don't exist. That's going to be resonant minus bandwidth over 2. And you guys will see this will give you minus 53.052, essentially. So yeah, so there is a bit of a problem with this exercise. Still getting the feeling there's something a bit off here, but just checking the formulas in the text, or using the formula from the textbook. So, but yeah, but in example 9, or rather example 8, that's done correctly. So I'll go show you guys. But yeah, but you shouldn't be able to get a negative frequency. But I think that exercise is just going to work out that way. So I don't think the values given there are the correct values. I think the resistance is too high. So if we maybe half the resistance, that might work out a little bit better. So let me just quickly share my screen to the textbook, and then you guys can see what it actually looks like. So example 8 on page 134, according to Perlego, or 126 according to the hard copy of the textbook. So you guys will see there. This one, yeah, so this one works out a little bit better. So yeah, so you have there's your bandwidth. So here in this case, what is nice is your bandwidth is actually less than your resonant frequency. So you can be pretty much sure that you're not going to hit a frequency on your lower end that's negative. There we have your lower frequency, there's your upper frequency. So yeah, so this is essentially what was supposed to happen. But yeah. And yeah, then you also have your other calculations here as well. So this actually, yeah, so this is more um, similar to the example I have in the slides. Right. Okay, so then, yeah, so then the exercises follow. So you guys will see with the RLC networks, not really, um, yeah, it's not really actually that, um, it's not too wild. It's pretty much the same stuff over and over and over again, basically. Right, and I see we pretty much just have 4 minutes left of the class. Um, right, okay, so any questions from you guys? Right, cool. I think I'm gonna end the class here. Um, seeing that, yeah, you guys have ample examples with the RLC circuits from the slides, and I'm pretty sure you guys can handle that. It's pretty much just a repeat of N4. Um, but yeah, I think that's it for tonight, guys. Have a good evening. I'll see you guys next week. Cheers.